Okay, recall that bar resolution comes very naturally from particular cell decomposition of the classifying space. So we take our standard model for the classifying space, which we have already discussed, points with labels on interval 0, 1. So we have points with labels in the group. Let us use agreement that particles disappear in 1 and not disappear in 0. This is EG. G acts from the left by multiplying label of a particle at 0 by group element, and so in BG particles disappear in both ends. Well, okay. And I recall that this, if we prescribe here some labels, then and label G0 in 0, then this was just notation for this particular cell, for all configurations that correspond to these particular group labels. Okay, and we have standard boundary and so on. What do we need to write explicitly multiplication in cohomology using this bar resolution? What we need is just we need a map. For x we take BG. So we need a map from x to x times x, from BG to BG multiplied by BG. But what is the difficulty? The difficulty is that, okay, if X is a cell CW complex, then we have such diagonal map, but this diagonal map is never cellular. Okay, it is not cellular even if X is an interval. We get diagonal of the square. This is not a cell. So to write explicit formulae, we need to choose a cellular approximation for diagonal. So we need to choose a diagonal, a mapping from BG to BG cross BG, which is homotopic to the diagonal, but which is cellular with respect to our multiplication, or which is cellular with respect to our decomposition. A natural way to construct such cellular, such approximation of diagonal is to start with the corresponding mapping for EG. For EG, I don't want to worry. This one will be delta prime, and this one will be delta tilde, for instance. Okay, and delta is true diagonal. Here, I would like the delta tilde be J invariant. With respect to which action? G acts on EG, and G acts here diagonally. So here it acts on both summons. Why this is useful? The matter is that here we do not want to worry about the condition that this should be homotopy equivalent to the diagonal. The matter is that EG is a contractible space, so all maps are homotopy equivalent. So we just need a map like that. It will be automatically homotopy equivalent to the diagonal. But now, in EG, the diagonal is G invariant, and our map is also G invariant. And in fact, we would like to, we need to worry about homotopy equivalence. We just need to worry that it is also G invariant. But it is not so hard to make it G invariant, and then we will get our map. I don't want to just discuss general situation. Let us just invent one map. What is the best possible way from EG to EG times EG? What is what can be a natural idea? A natural idea is to divide our segment into two segments. Just we can divide it by 0.1/2 and separate it into two segments. And then, well, okay, make homotopy of each of them to get, again, the segment 0, 1. So, question, is it a good mapping? Suppose that, okay, I start with some configuration of points here, points with labels, and I proceed as follows. Unfortunately, no color, but okay. I just make a cut at 1/2, and I just take all, make a homotopy for each of them, so both of them get, and okay, I get such a point in the product. Here are these. I can write it by a formula, but I don't know. I think that it is. I think it's completely clear what is happening. But the question is whether this is a good answer. Whether this map is well defined, whether it is equivariant.
Because it's not good. For example, a point on 1/2 can be in the left one or the right one.
Yeah. This is a very bad map. If a point, look, some point GI is here, and it travels there. Okay, there is no problem here. The point comes to 1 and disappears. No problems. This is continuous. But here, this particle appears, and we have no way to disappear, or particles are not supposed to born or die in this 0. They are allowed only from this. But there is a very good way to we can somewhat improve this construction, and the improveness is very easy. I would like here add a particle in the end, at the end, and this particle will be with label equal to the product of all labels here. So I take all particles which get into a semi-open interval here. For instance, they are G1, Gi, even not into semi-open, or even to closed interval. If a particle is here, we also get. We take the product of their labels in this particular order, and this is additional particle which is added here. But all further particles, gi plus 1, gk, they are now, this is well defined. Look, when a particle, again, the only thing we should worry about is when a particle approaches 1/2. If a particle approaches 1/2 and goes from left to right, yes, then here it disappears. But here there was a particle. Here on the right, what happens looks like that. We had a particle g1, gi, but when this particle moves to the right, then we have two particles. The first one with label g1, gi minus 1, and very close to each there is a particle with label gi. This is a continuous process. So here we have no problems with continuity. This is the end. Moreover, this map is G-invariant. Now it is G-invariant. Without this, it will not be. The matter is when we multiply this label by some G, then this G is added here, and it is added here as well. So it is G-invariant.
Sorry, and what if we have in 1/2 some gi plus 1, for example?
Particle which is in 1/2 is also counted here. So okay, it will be here, and it will not be here since particles disappear in 1. We have no problems in this. Well, look, this particular map delta tilde. This is delta tilde. It is invariant. It is what it is. It is well defined. It is invariant, and it is cellular. Look, if we start with I prefer to add here. We already discussed that it is convenient to always think that there is a particle at 0, maybe with label 1. So I prefer here to have this G0 at 0, and then it is here. Well, how it goes? What is the induced? Look, if you have here a particle in k-dimensional cell, then here we have I, and here we have k minus I. So totally we have a cell of dimension again equal to k. And moreover, it is easier to write down how this map, what is the induced map in the chain, into cellular chains. Well, it is just written from here. The result is like that. Here I write G0. I consider this particular cell. And this cell goes to, okay, inside this cell, particles can be divided into two parts in several ways. And each of them, this means that this cell travels along several cells of the product. And the result is here, like that. We take the sum from I from 0 to k. The left cell is like that, up to gi. And here we have g0, g1, GI, sorry, and here we have GI plus 1 GK. So we have such a nice formula. Usually this formula is written without G0. Since we know that it is G invariant, it is enough to write a result for G0 equals 1. So usually in handbooks you can meet this formula, and it is completely enough to know when we know that it is G invariant. Well, we have such a nice formula. Well, what we have not seen yet. Delta tilde is, of course, it is homotopic to the diagonal, but one can ask whether it is equivalently homotopic to the diagonal. In fact, it is automatical, but in this particular case, it is very easy to see this homotopy, directly. Namely, what is a diagonal? We just take this segment and repeat it twice. Well, how to make homotopy from repeating it twice? Here we repeat it twice. And here we proceed like that. So homotopy from here to here looks like that. We start here. We take this point and say that it travels along this. We shorten this. We make it shorter and shorter and shorter, this segment. And we make it in the following way. This point travels and eats these particles, so particles disappear. And at every moment we make a homotopy, which again makes this segment 0, 1. So this travels from the whole segment to the half of it, just eating all particles from the right. And here we take this particle and it moves to the left, and again it's particle, but here it remembers which particle are already eaten, and it multiplies its label by them. And we again arrive to this. So this is just a direct homotopy from usual diagonal to this one. Okay, and yeah, of course. No. Here we do not have GIs. So when we travel, we add just this. Instead of adding G0 till GI, we add G0 inverse till GI inverse. No. For example, if GI goes to the right, we want it to be cancelled. So it must be GI inverse. No. Look, when GI crosses this, yes, then this particle GI is separated from the previous particles. We had a new particle appears, and here we have smaller. So it is not true if we write it versus it doesn't work. So it is correct formula, this particular. Okay, just a good algebraic exercise. You can check purely algebraically, without any appeal to topology, that this map is a chain map. Just we have a differential in bar complex, and you may just compute this differential and check that this delta tilde is a chain map. Well, I would like to formulate this and even one more exercise. So first exercise is that this delta tilde is a chain map. Actually, it follows from what I said, but an exercise is to check it directly. But second exercise is, in fact, the following. Suppose that we have any projective resolution, let f star be projective resolution, not maybe bar resolution or any other projective resolution for z over zg. Then we can take any chain map from F, the only way that it is G equivalent chain map. So it can be any G equivalent chain map. The only restriction is that, okay, resolution means that we have a map from E to Z, from F0 to Z. It should commute with augmentation, with this augmentation homomorphism. So any G equivalent chain map that commutes with augmentations provide us the right multiplication in cohomology. Provide us with so we can always take the quotient by G action, and in the quotient we get a chain, so with approximation of diagonal from on coinvariance. Okay, I prefer to write it like that. And hence, so sorry, here we have tensor product. And hence, it provides right multiplication in cohomology. The same, all such chain maps gives the same true multiplication in cohomology.
Who are the epsilon and C?
Projective resolution always comes with a map from F0 to Z. Just from definition of.
Yes.
And I just denoted by epsilon. So we only want this chain map to be compatible with these augmentations. This is the only restriction.
This is only one
The restriction?
in the resolution.
Yes, yes. The last one to that. Okay. So actually, the fact is that this is the only thing which we need to check. We can skip all this topology and just say, okay, this is a chain map, so it yields us a correct multiplication. But in this particular situation, we have this nice picture that actually this comes from, this is indeed a good homotopy approximation for diagonal. Okay, what I want to say next is that, well, of course, we are interested not in EG, but we are interested in BG. What we see in BG is immediate from here. We just need to erase this. In BG, all cells each orbit of cells are glued into one cell, so we just need to erase this. And the corresponding cellular map in BG.
So here we say that this lower map is homotopy equivalent to the diagonal.
Well,
What does it mean, approximation of diagonal? Means that this lower map is homotopy equivalent to the diagonal.
yes, the matter is that for a chain complex, we do not know what is a diagonal itself. For
But we do know what is the diagonal in this sense.
well, we cannot map x to x tensors x. This is not diagonal for chain complex. But actually, we can say what is an approximation. We do not have true diagonal for chain complexes. For topological spaces, we have, but it is not cellular. But for chain complexes, we do not have true diagonal, but we have approximation. This means, what does it mean that a map from x to x times x is homotopic to the diagonal? This means that if we take projection with to the first projection, then this map is homotopic to the identity. And similar for the second map projection. And in this sense, we can say what is an approximation for the diagonal, though we do not have a diagonal. So a map is an approximation for the diagonal if we compose it with any of the two projections, and we get a map homotopic, chain homotopic to the identity. This is a correct way to say what does it mean, an approximation for diagonal. So in particular, all approximations for the diagonal are homotopic to each other, and they yield the same multiplication. And this is the multiplication we are interested in, standard multiplication in the group cohomology. But the matter is that any projective resolution and any G-equivariant chain map can be used. And we always get the same multiplication. Okay, but this is an exercise, but for this one, we see this completely, that this one is good. Okay. So, I would like to write this formula. So, for in cellular maps, now let us denote, now Fk be the cellular chain group of EG with our standard subdivision. Then this is our usual normalized bar resolution. So I prefer to write this. Okay. And then the coinvariance, or the same, is Fk tensor product over G with Z. This is the cellular chain groups of BG, of what is below. This is just as we discussed. And here the corresponding cellular map is just, once more, it is the same formula without, with erased these terms. So I prefer to write it down explicitly. It is sum from I equals 0 to k. Here we just divide our tuple of group elements into two parts. Okay. Once we have such a simple formula, okay, what is, once more, as before, I prefer to use notation Ck of G with coefficients in some commutative ring R is just by definition home from this fk to home over zg of this fk to r. And if I will always assume that the action of g on r is trivial, so we do not have local coefficients now, only untwisted coefficients. And then I recall once more, we already discussed it last time and before, that this is just function of g elements in G. Well, so an element here is just a function from basis in the corresponding chain group is given by such tuples. So it is just function from k elements of G, but not a homomorphism, only a function to R, and we have standard differentials and so on. And how this we need to write the dual of this formula. So assume that we have a function in here and similar function b in Cm of gr, and then I can write down the product of these two functions, and it is, I need to compute its value on tuple of k plus m elements, and the result is just I need to take the value of A on G1, Gk, and the value of B on Gk plus 1. Sorry, in this situation, it is more natural just to write these elements in a row. It is usually written like that. So otherwise, the notation is too cumbersome. And we have here Gk plus 1, Gm. But this is it is not good to write it like that. The matter is that when we go to home, then and take home with tensor product, then some signs should appear, and these signs are usually when we change. The usual convention is that when we change in a row two elements of some degree, then we should get the corresponding sign. Here B was here, and now it is here. We make it go through k elements, so it is -1 to km, and B itself has degree m. So the correct formula is like that. And this formula is explicit formula for multiplication. So it is a formula on the level of cochains, on the level of functions on G, but in cohomology it induces the standard multiplication. But it is completely easy, and it is often convenient to work with. It is usually not used in for co-chains. Just when we take such a function, it is too cumbersome to write to right angles, so on.
But formally it is needed.
Just for instead of this, one usually writes like that. This is just the same. So just don't worry about it. It is not a considerable difference. Okay. A very good for those who knows the standard Alexander-Whitney formula in singular cochains, another situation when cup product is given by an explicit formula is Alexander-Whitney formula in singular cohomology. But it can be used not only in singular cohomology, but in any triangulation with ordered vertices. And this is exactly our case. So a good exercise is to understand that this is directly our EG and BG is not completely simplicial complex, but it is their cells are simplices. Just it is not a simplicial complex since some cells are degenerate. But nevertheless, the Alexander-Whitney formula can be written here, and it is directly as written here. So this one is nothing but the standard Alexander-Whitney formula. Okay. So this is what we should know about standard cup product. But also I would like to discuss one less standard product, which is, however, very useful. It is a so-called slant product. Or it is sometimes called skew multiplication. Well, the idea is as follows. It is a multiplication which mixes cohomology and homology in the following way. Suppose that we have two, I prefer always have coefficients in submarine. Suppose that we have we can have a cohomology class in the cohomology of a direct product, and we have a homology class in the second summand. Then we get into the cohomology in the first summand. It is the standard notation is slant. It is A slant B. Well, the simplest situation when this product appears, let us start with one particular with one particular case when the definition is very easy. Namely, assume that first of all the coefficients are in a field, and second that all our complexes are locally finite, which means not even locally finite. Well, their skeletons are finite. Each skeleton consists of finitely many cells. So we can have infinitely many cells, as for instance for RP infinity or CP infinity, but we have finitely many cells up to every dimension. And finite skeletons. In this situation, with coefficients in field, first of all, cohomology are dual to homology, and second, just dual vector spaces. And second, cohomology of direct product is just tensor product of the corresponding cohomology groups. But tensor product over this is direct sum of tensor product of, so HP of x times 1 is direct sum of I plus g equals pi, hi of x tensor Hj of y. Well, and for this product, the only important part is the part h pi minus q, hq here. And the idea is that we can extract this part and pair off this cohomology class with this homology class. And this is exactly what we do. So our class is uniquely determined by the following property. If we take A from here and C from here, then to characterize the obtained cohomology class, we need to pair off it with, we need to pair this class with various homology classes. And what we need to point out all such values. And it is, I would like to write it like that.
What does it mean that B is in C?
Sorry, C is here. I just will hurry up. And B is in the corresponding homology of X with coefficients on R. And this is a test class. Just to describe this cohomology class, I write down its pairing with different homology class. And I would prefer to write like that, but as usual, it is better to put here sign equal to degrees of B and C. Okay, in this particular case, if F is a field and we have finite skeletons, this can be taken for a definition. In general situation, this also can be taken for definition, but we need to say that this is true on the level of chains and cochains. And then it induces a well-defined on the level of chains, we have here tensor product. We should pair this tensor product with cochains in Y with chains in Y. They pair off, and we get into cochains of X, and just by the same formula. And this induces well-defined multiplication and cohomology. This is a standard check that we have this notation. Okay, and now before we well, the second part today will be devoted to the special case I would like to discuss slightly. What can we say about homology of symmetric group? Actually, this is a situation when the answer is known, but it is rather complicated, and I'm not going to give, not only to prove, but to give this answer. However, I will show not what is the answer for symmetric group, so we may just ask what is the homology of symmetric group. Okay, we can take any coefficients, for instance, z coefficients. It is clear that what is the answer for q coefficients? We have already discussed this. This is a finite group. So if coefficients are in field of zero characteristic, then or in any abelian group when we can divide by integrals, then or even in any abelian group where we can divide by the order of the group G, then the coefficients, then the homology is like the homology of a point. So we have trivial homology, except for dimension 0, where it is Q. So for finite group, nothing interesting with Q, but we can, Z is more difficult since it is not a field, but we can take different various Fp here. Well, the answer is known, but I don't want to go, I don't want to discuss this, but what I want to discuss this is how can we use a homology element. Suppose that we know a homology element of Sn with some coefficients. What is a useful application of such an element? And a useful application is as follows. Just now I just say some idea, but we proceed further after a break. Suppose that we have an arbitrary CW complex X, and we have a cohomology class of it. With coefficients in some field. F is field. And I assume that C is also with coefficients in the same field. Well, actually all these restrictions are just for simplicity. We can take not a field but something else, but just I would like to consider a simple situation. What can we take? Can we do? This CW complex knows nothing about the symmetric group. It is just CW complex without any group action or anything like that. But we can do like that. We can consider the product of n times the nth power of this X. And this space, why it is interesting? We have a natural Sn action on it. Just by permuting the summons. And what do we see? Actually, when we have here a cohomology class, we immediately obtain the nth power of this cohomology class just with respect to cross multiplication. So of course we have the class, this is nth power with respect to cross multiplication. This is a cohomology class in Qnth cohomology of this space with coefficients in the same field F. But what can I say? I can say that if I can choose here any particular cochain representing this cohomology class C, U. Let us take for A is a cochain, cellular cochain representing U. Representing U. Then the corresponding cochain A to the power n can be written explicitly. How? The value of the cochain an on any cell in this nth power has such form, and this value is okay up to certain sign, which I don't want to write down now, but which can be easily written. Okay. In fact, here we have q times n over 2. Well,
what are the sigmas?
Sigmas are cells in X. Any cell in the power in X to the power n can be written as product of cells.
Are they random dimensions?
They are random dimensions, but the value, I complete the formula. The value is non-zero only if all these sigmas are q-dimensional. Otherwise, this pairing is zero. All values which makes no sense are zero. if we cannot apply A to the corresponding cell, then it is just 0. Okay. So, look, now I claim that this cochain is equivariant. What does it mean? If I apply Sn x here, and cochain is just invariant under this action. It is not completely true. It is invariant up to sign. But I prefer it to be truly invariant. What restrictions should I impose? This is just technical restriction. We can proceed without it, but I prefer not I don't want to work with cohomology with local coefficients, and that's why I prefer to impose these restrictions. If I want this cochain to be truly invariant, then I must either require that Q is even or require that the characteristic of F is 2. In both cases, signs disappear. When Q is even, then permuting any two x's doesn't change this A. When characteristic of F is 2, then no signs at all. So we assume that either Q is even or characteristic of F is 2. This is just technical assumption. Then this A is truly invariant. And what can we do? Actually, at the moment, I would like to discuss one more important concept. It is the concept of equivariant cohomology. What is this?
Why isn't it invariant, right?
Well, why it is invariant?
Isn't.
Because when we swap to sigmas, some sign appears. But if sigmas are even dimensional, then it's okay. It's always invariant up to sign, but assume for a moment, let us forget about this situation just for a moment, and assume that a group acts on some space Y. Look, there is an important situation. Sometimes, if the group acts on Y, then we of course can form the quotient space. But its cohomology or homology often knows very few about Y and about action. This is not very good example, since the action may have stabilizers, and taking quotient can be not very good space, and it is not convenient. It is much more convenient to have free actions. When we have a free action, then quotient space knows more about Y, and for instance, if the action is free, then this is a covariant, and we know a lot of topological things about covariants. But if the action is not free, there is not so good topological relation between these two guys. But sometimes we have an action which is not free. So a good idea is to make this action free without changing our Y homotopically. So we would like to have homotopically the same action, but now we would like it to be free. What is the best possibility? The best possibility is to multiply y by a contractible space with the action of g. And consider here the diagonal action. So g acts both here and here, diagonally. This one is contractible, so we don't, homotopically, we do not change our space. But now this action is always free. And so the quotient is very good. And it is natural to consider a quotient. So we may, this quotient is usually denoted by, in the following way. It is just by definition the quotient of y with Eg, quotient by this diagonal action of g. It is sometimes called the Barrel construction. And by definition, the equivariant cohomology of y with respect to the action of a group G, it is by definition the homology of this Barrel construction. It is a standard and easy, a rather easy exercise that this one is independent on particular choice of EG. So we can have many different EG, many models for it, the various contractible spaces on which the group G acts. So the result is independent on EG. Actually, this space is up to homotopic equivalence independent on the case of EG. So the cohomology, so this is usual cohomology, this is equivariant cohomology. So the thing which we discuss in somewhat more details after a break. Now it's time to do a break. But if we have an invariant cochain, that it always gives us an equivariant cohomology class. Let us discuss it after the break, but I claim that this u to the power n can be naturally thought about as the nth cohomology class, not nth, it is qnth, yes? Qnth cohomology class of what? In equivariant cohomology of this xn with respect to the symmetric group. With coefficients in f. Now, of course, this construction is functorial. It is very natural. Of course, it's functorial. So we can apply the diagonal map. We have a diagonal map from x to the power n. Look, this one, of course, it is functorial in the category of G spaces, of spaces with the action of G. Here we have natural action of the Sn, which permutes summons, but here we have trivial action of Sn. So, okay, we get this delta yields us pullback, which goes to the equivariant cohomology of x itself. But now let us ask ourselves, what is equivariant cohomology in the case of a trivial action of G? If G acts on Y trivially, then, and this is exactly our case, if G acts trivially on X, then we just take the quotient of EG. Our quotient doesn't affect Y at all. So this space is just X times BG. Nothing but. So this one is just the same as Qnth cohomology of X times BSN with coefficients in F. Okay, and now we apply slant product. This is something which I introduced to apply. So we have, from the very beginning, I start with a homology class in symmetric group, and I haven't used it yet. Now I would like to use it. I take the slant product with homology class C, and I get into the cohomology of the first summand of dimension Qn minus I. And look what we get. From the very beginning, we started from a homology class in the qth cohomology of X. We do something, we make some natural things, and we arrive to a cohomology class in this homology group. What we get is called a cohomological operation. So we obtain a natural way to build a new cohomology class starting from, so this one is fixed, this is just fixed. And now we have a natural way to produce a new cohomology class. So this one is a cohomological operation.
Why u to the power of m lies in?
This is the thing which I said that we will discuss after the break.
Okay.
This is the only thing which I don't explain properly. So now let us make break. Maybe we resume at 6:5. So 5 minutes past 6. But now let's make a break. But after we understand this, we just arrive to a cohomological operation. And it is a useful thing, and we will discuss it further after the break. Знаете это? Конструкция Стинера. Это операция Стинера. Вот он так и строил. Причем он гомологии сцены не знал. Это, это на настоящий момент полностью вычислено, сейчас нет. Но в тот момент еще не было. Вот. Да, конечно. Well, let's continue. For the second part, I hope that I'm not going to give a lecture. I hope that we perform some computations together. Well, but let us start with this discussion. This discussion, I was very brief at this point. Why this? Sorry. Why this u to the power n actually can be interpreted as an element of equivariant cohomology. I describe it in a moment. Look. So we have discussed that our cochain, this cochain representing this cohomology class, is invariant. We impose this condition just to be sure that it is invariant. What does it mean? It means that this cochain belongs to Hom over the group ring ZSN from chain complex of dimension nq to F. Okay? This is not well, this cochain complex, we can consider this cochain complex where here we have star. Yes? This cochain complex is not the complex which computes the equivariant cohomology. But let us write down which complex computes equivariant cohomology. This is the cochain complex of this space. But, to say that we have a chain on this cell CW complex is the same as cochain, is the same as to say that we have G invariant cochain here. The action is free, so we just have G copies of each cell. To say that we have an invariant cochain here is the same as to say that we have cochain on the quotient. So our cochain complex of this space, which is interesting to us, well, it is the same as cochain of invariant complex of invariant cochains for this complex. So this is the same as Hom over ZSN. Or it's I do not have enough place here. This is the same as Hom ZSN from C star of xn times Eg F. This is completely the same. Now, of course, we have map of chain complexes. C star of xn times Eg maps. This is just the tensor. This is the same as tensor product of x with just resolution. C star of Eg is our free resolution for G. F is just C star of Eg. Y is, sorry, for why I take this xn, x to the power n. And here also we always have x to the power n. Well, and of course we have a morphism from here to c star over xn. Oh, I'm sorry, I have two different f's. Let it be p. This is a resolution for, I'm sorry, I use the same letter for field and for resolution. Let resolution be p. Okay? So p star is our usual resolution for z over zg, which is just cellular chain complex of Eg. And we have such, and here we just have augmentation. P star goes to. Okay, this means that we have arrow in this direction on the level of chain complexes. So in cochain complexes, we have arrow in opposite direction, so from here to here. So what does it mean? If the action was free, as we discussed here, if the action was free, we just could define equivariant cohomology by means of invariant cochains. We just may take all invariant cochains, and these complex immediately produce equivariant cohomology. When the action is not free, this is not true. However, this is true in one direction. If we have an invariant cochain, so an element here, it still produces an element here, so a class in equivariant cohomology.
Should there be a star anyway
well, yeah, yes. Here is star, but an lives in particular dimension, which we know. But generally, this is general situation that if we have an invariant cochain, then it always produces an element in the equivariant cohomology. It is not true that all elements in the equivariant cohomology are produced in this way, but in one way this is true. So invariant cochains produce elements in the equivariant cohomology. That is why, but our cochain is invariant. So we arrive to an element q to the power n. Then we apply delta star, get into here, and apply length product with c, and get there. Of course, it is not interesting to take c equals to 1, since we arrive just, then we can forget about this. Yes, this is slant with 1 is just projection onto x, and we arrive to un itself. Oh, well, we knew before that we can take the power of an element. We do not need all this stuff to make this once more. So c equals 1 is not interesting. So we are interested in non-trivial, in high dimensional, not zero dimensional homology classes of symmetry groups. Okay, we do not know. People know how to compute homology of Sn, but this is not easy. But we do not know at the moment. But okay, if our goal is to obtain some cohomological operation, and it is always useful to have some cohomological operation, to have something natural in some operations natural in a cohomology class, then if our goal is as it is, then it is not necessary to study all classes. It is just necessary to produce some classes, homology classes. Once we can construct a homology class in Sn, we get a cohomological operation. Well, actually, at this point, I must say that indeed what I said, this is construction due to Steenrod, and this is his construction of reduced powers. Actually, they are reduced powers since we reduced the power by some class C. Now let us understand, to use this construction tool, we need to understand how we can produce homology classes. Well, and the main idea is that symmetric group is difficult, but cyclic group is much easier. And for cyclic group, we have already discussed the homology of it. Now I would like to remind the result and how we get this result. And okay, what is the relationship between cyclic group and symmetric group? Of course, we have a homomorphism from cyclic group of order n to symmetric group of order n. Just we have a we have the subgroup generated by maximal cycle in a sense. So, of course, we have corresponding homomorphism in homology. Let us just, I say that we consider the simplest possible case. The simplest possible case is that I take here prime P, and I take homology and cohomology with coefficients in Fp, infinite field of P elements with the same P. So this is our situation. And of course we have such morphism, homomorphism. And so once we know this homology, I will remind it in a pair of minutes, then we can get some classes here. I do not pretend that this is all classes or etc., but we can produce something, and we can use them to construct cohomological operations. Just one remark. One remark is about this. As I described in the case of characteristic F not 2, literally this construction works only if our class is even dimensional. If the class is odd dimensional, still everything works in the same way, but we need to take here not untwisted coefficients, but twisted coefficients where Sn acts on F by sign. I don't want to go in details with twisted coefficients now, but I just want to say that this is not an important restriction. This is not a restriction at all. Just without this restriction, we need to apply more technique. But still, everything can be done. But at the moment, let us assume that our class is even dimensional. P is prime, and everything like that. Okay. So, I want to remind how the homology of cyclic group looks like. I recall that for the cyclic group, we can let Cn be a cyclic group and let T be its generator, and P is prime. Then I recall that we have the following resolution, much simpler than bar resolution. We have a resolution for Z over, first of all, what is the group ring? The group ring is just the polynomial ring it is convenient to use, well, in this notation, quotient by such ideal. So we have the following free resolution for Z over ZCP. We have just one generator at every dimension. So this one is E0, E1. These are just generators of these one generator for free modules. Well, over this ring. And the boundary operators are written as follows. Where delta is just t minus 1 and sigma is the sum of 1 plus t plus t to the power p minus 1. Well, this is just very explicit answer. If we write such such a resolution, then I claim that this sequence is exact. So this is indeed a resolution, a free resolution, and we can compute the cohomology of the group. At the moment, I want homology rather than cohomology, homology of the group CP by applying this resolution. What do I get if what do I need? I need to take the resolution. So resolution is this sequence without this last z. I want to take tensor product of this resolution over ZCP with z. Well, what I get? I get z in every position. And these z's are, well, with some misuse of notation, I use the same E0, E1, and so on for denoting the generators of these z's. Okay? And these formulae, these are formulae, well, let this resolution be P star, yes. And this is P tensor by Z. Okay? Oh, no. I don't want to have tensor by Z. I would like to work with coefficients in FP, in ZP, in the field of P elements. So I prefer here to have FP, well, and so here also I would like to have FP. But over Z it is also possible, but at the moment I prefer to do this. But look, over FP, both these elements, what does it mean? We tensor over ZCP with FP. So all group elements go to ones. And these two elements go to 0. This one just t and 1 goes to 0 and to 1 and we get 0. And here we have sum of p elements, p identical elements, and we again get 0. So here, all differentials are just zeros.
Why t goes to 1?
T is a group element. And what does it mean that we take the tensor product over group ring with FP? Or any group element multiplied by generator here gives generator itself. So we can get rid of all group elements. So So the homology in each dimension is just generated by this EI. So we have we see that homology of the group CP with coefficients in FP is FP for each I greater than or equal to 0. Well, and what we are interested in is well, and this is generated by EI. Well, our goal is to consider the corresponding cohomological operation. Just one remark. We always, there is such usual thing which is called Bach-Stein homomorphisms. We can consider such sequence of coefficients, of groups of coefficients. And we know that both homology or cohomology groups, such sequence of coefficients group induces long exact sequence of homology groups. I write for homology, but the same for cohomology. If I take the homology of any space X with coefficients Zp, then let it be I and let this be J. Then we get into, using I star, we get into the homology of X with coefficients Z over P squared. Then by G star, we get in homology of X with coefficients with ZP. Well, this is this ZP and this is that ZP. Actually, this is true for any exact sequence. So, and here we have this. It is called well, it is called Bach-Stein homomorphism. It is denoted by beta. This homomorphism which arises. And so on, we get this. We have this long exact sequence, and what appears here is called Bach-Stein homomorphism. And in fact, it is not hard to compute Bach-Stein homomorphism here. Well, what is the Bach-Stein homomorphism of, what we need to do? We need to find for our class a preimage. Well, we can do it in coefficients with Z over P squared, but actually we can take a preimage with coefficients in Z instead. Well, if we take e to the power 2I and take its look on this chain, not in coefficients, not as on the chain with coefficients in ZP, but as on the chain with coefficients in Z, as I wrote initially. If I take here Z, then what we get? We get that over Z, the boundary of E to I is not 0, but it is P times and the definition of Bach-Stein homomorphism is just we need to divide by P, and this is the result. The result is always divisible by P, since it is 0 in Z with coefficients of P. Here it is 0, but over Z it is not 0, but it must be divisible by P, since it is 0 when reduced by p. So the definition of that Bach-Stein homomorphism is exactly that we need to divide this by p and then to reduce by p. So let it be an exercise that Bach-Stein homomorphism of e to I is e to I minus 1. This is an easy exercise. But what is not so easy, but still I want to leave it as an exercise, what is not so easy, is that in fact, we can ask, assume that initially, well, we have our construction for a class C, but assume that initially we take Bach-Stein of C. What is the relationship between this and that reduced powers? We can use C to produce cohomological operation, but we can produce an operation using beta C. And the answer is as follows. That the result for Bach-Stein is up to certain sign. Sign can be written explicitly, but I don't want to do this. It is Bach-Stein of that element. So, but this one is cohomological Bach-Stein. It rises in dimension by 1. Okay, this exercise shows that it is not so interesting to take classes which are Bach-Steins of something. Well, the result will be also Bach-Stein. Bach-Steins are the easiest cohomological operations, and we more or less can work with them. So it is enough to study those which are not Bach-Steins of something. And these are these. So it is enough to take C equals E to I. Then using this exercise, we immediately get the answer for e to I minus 1. So the interesting case is C equals to E to I. So this is what I'm going to take. And this is what Steenrod took. But now, well, the first question, well, what does it mean? So we have here 2i homology. Here e to I lives. But we are interested in homology of symmetric group. We get into 2i homology of symmetric group. And of course, the first question which we should ask is whether we get 0 or not. If we get 0, then we have no interest in cohomological operation. If we do not have 0, then we can hope that a cohomological operation is interesting.
What is C and beta? Beta I can see what
Here C is any homology class, and beta is Bach-Stein homomorphism.
Yes.
But C is any homology class. Just we can use this operation starting from any class C, but then we can define this similar operation using class beta C. And we can ask what is the relationship between them. The relationship is very easy. Well, that is why, so we concentrate on this case. Okay. Now. So, actually, what we are interested in? We are interested in this particular homomorphism. Steenrod denotes it H to I, just this homomorphism. And let us also use this notation. H small 2I is just this particular homomorphism induced by the inclusion. Well, and now
why is the A is the index? How is A related to the right side?
A, this one.
Yes.
This is 2I, sorry. Sorry for my writing. This is not A, this is 2I, this is just this index. So, proposition. This homomorphism, H2I, is trivial whenever 2I let us, there are two cases here. P can be 2 or P can be an odd prime. The results are slightly different. So let us concentrate on the case of odd prime. I just, okay, there are analogs for P equal 2, but I don't want to consider two variants in all situations, so assume that it is odd. H2I is 0 whenever 2I is not an even multiple, is not an even multiple of P minus 1. In other cases, well, so this can be non-trivial only if E is divisible by pi minus 1. This is the only situation when, in all other situations, just the homomorphism is trivial. And we have not so much amount. No, we have some amount of time. I hope we soon understand this. But just for those who ever met standard operations, I just would like to write down the answer. Well, the standard operations in modern notation, which in fact was introduced by standard itself. There are such operations PS. PS are operations raising power by two S times P minus 1. There are such nice cohomological operations. They are stable, they commute with suspension, they are very nice from various points of view. And the idea is that, so I prefer here to write Q and here to write Q as well. Well, so the idea is that if one wants to write down this PS on U, which U is Q-dimensional, then I need to do as follows. We take some sign. So, in fact, the idea is that it is exactly those operations, but we need to normalize it for convenience. But the normalizing multiple is rather unpleasant. But still, I just write down the answer. This is binomial coefficients Q of 2. Here it is m factorial to the power 2s minus q. And here we have UP reduced by the class with such number. well, where m is p minus 1 over 2. So, okay, essential part is this. So you need to take u to the power p, and you need to reduce it by the class with such number. N is p here, sorry. M is p minus 1. N,
which is,
there is no
no
n. It's p. Yeah. It's p. I'm sorry. This one is.
It's SP.
Yes. This. Yes. Permutation group is SP. So, and these are exactly those for which. I said that we need to take. If we don't want to go in more technique, we need to take only even q. So this is exactly even multiple of p minus 1. So exactly those which are not 0 give such operations, which are called standard operations, and they satisfy a lot of nice properties and so on. This is just some normalized coefficients. It goes from computation. It arises from computation. The matter, the main idea is that when u is when the dimension of u is 2s, we would like to have ps of u equals u to the power p. We would like to have this, and if we don't use such coefficient, we will not give correct, we will give u to the power p with some coefficient. So this coefficient is just to normalize this. It is easy to see that this coefficient is non-zero modulo p, so this is just some invertible element which can be computed explicitly and which was computed explicitly. And these operations are convenient, but they arise in this way from homology of symmetric groups. Nowadays there are plenty of other constructions, but still this was the original one. Well, what I want to discuss, I want to discuss things which are related with symmetric groups. I don't want to go in this very deeply. I just hope that you can treat the flavor of this, and you can go in details if it is interesting to you. There are two good well, how it is called, sources where you can read this. One of them is a book by Steinert and Epstein, Cohomological Operations. And or Introduction to Cohomological Operations, I don't remember exactly. And another one are several original papers but by Steinert, which are also very well written. Okay, but at the moment, let us discuss what we can discuss now, and what is more or less related to homology of groups is this proposition. Why this is 0 for some, except for several cases. Well, why I want to concentrate on this? Because here we have a general situation. Sometimes it is convenient to have some tools to prove that images of certain homology classes into larger groups are trivial. Sometimes it can be useful not only in this situation but generally. Let us discuss what tools do we have. What is the main idea? The most important, well, and here is of course P, I'm sorry. the main idea is that the group is not normal. The subgroup is not normal. Well, it is not. It is not so important that it is not normal. Another thing, another detail is important. Okay, the more important, even in fact, it would be even easier if it were normal. But the idea is that if we have, suppose for a moment that we have a normal subgroup, we have a group and we have a normal subgroup. Then this group acts by conjugations on this normal subgroup. Then it acts immediately on homology and cohomology of this subgroup. This action on subgroup immediately yields action on its homology. But the action of the group acts on itself by conjugation, but the action of a group on its own homology is trivial. This is an important point. Let us understand why this is true. So, the most important claim is, this is true for any group, that action of G by conjugation on homology of G. I mean that G acts on conjugation on itself, but we induce the action on homology of G, or on cohomology, but let us speak about homology now, is trivial. First of all, how this action can be written, for instance, in the bar resolution. This is action by conjugation. So in bar resolution, any homology class can be written by a cycle of the form some sum of elements of such elements with certain signs or certain coefficients. Just, I don't want to, I must say what is sum about. It is about some index, okay, some index lambda, and here we have lambdas. So this is just index. Okay, we have, and here we have some coefficients dependent on lambda, something like that. It's a general. So after action by an element G, if we conjugate by an element G, we get the same sum, and each element is conjugate. I claim that this action is trivial. How one can see this? This can be seen directly from bar resolution. This can be seen from general understanding without any particular resolution. But still. Well, for instance, if we speak about first homology, then it is an obvious thing that any group acts trivially by conjugation on its abilization. It is trivial. But the same is true for any homology.
First G and the last G can disappear, and the middle G and G inverse collapse.
You say that this will be exact. If this one is a cycle, then this one is also a cycle. But the question is why it is a homologous cycle. Well?
Because I mean, we can separate. Like, for example, the first G and the last G inverse can go because we are on BG, so we can take them out. And they will.
Yeah, yeah. We have such a homotopy. In this, yes, in the standard model, you can here, if you have here such elements, yes, you can separate each such particle into three. The middle has Gi, here we have G, and here we have G inverse. And then this particle began moving and they disappear, they cancel, and the last and the first goes and disappear at the ends of. This is how it can be seen in the standard model of a bar resolution. But I would like to say that actually, this is a very standard fact about topological spaces. If you have got a topological space, then its fundamental group, fundamental group can act on homology of fibers in some fibration over the space. It happens that the fundamental group of a base acts non-trivially in homology of fibers. But the fundamental group cannot act non-trivially on homology of the space itself. But here is exactly this situation. The group acts in homology of the space. The fundamental group of this space cannot act on homology. Well, the matter is that action of the fundamental group on homology is just pushing this homology class along such path. It adds nothing in homology, so the result is trivial in homology. Okay, but okay, there are plenty of ways to understand this. Just it is useful to understand that there is such wonderful fact. It is very easy, but it is very important. But it is not true that group acts trivially on homology of subgroup. So this is some equation. Once we find an element of a group which acts by conjugation on subgroup, then any homology class, and we know particular homology class here, and its image under this action, they together, their difference definitely goes to 0. And we can use this to understand something. But the matter is that, of course, the group is not normal. The group is not normal, and so we cannot take here an arbitrary element. An arbitrary element doesn't normalize the subgroup, but we need to take an element which normalizes the subgroup. However, we shouldn't take element from the group itself, since if the element is from this subgroup, then of course it acts trivially on its homology and we get nothing interesting. But it is interesting to find another element which normalizes this subgroup. And okay, this is the first question. So we have our, it is natural to identify this group CP just with SP acts on standard on residues modulo P. Well, it is more convenient to have residues from 0 to P minus 1 than from 1 to P, but this doesn't matter. And okay, CP is generated by this this cycle, which goes 0 to 1, 1 to 2, and so on. Which element should we take in normalizer? which good elements lie in normalizer of such subgroup. So I would like to introduce a permutation gamma, which normalizes this subgroup. But it doesn't lie in this subgroup. What can we invent here?
Sorry, what is T? Is this CP or?
T is just a very standard cycle in CP. 0 to 1, 1 to 2, etc., 2 pi minus 1, and back to 0. This very standard cycle, just adding 1 in the field FP. Now, let us invent something which normalizes this group.
What's a normalizer?
Normalizer, well, we would like that conjugation by gamma takes this group to itself. The group is not normal. If it was normal, then we could take any element. Now we cannot take any element. We must take such element that the conjugation by it takes the group to itself, the subgroup to itself. Well, yes, that's the right. I would like to consider such a permutation. This is Ks, of course, modulo P, where K is fixed. One important point which makes it easier. It is even better to take for E, I forget this in English. I write it down, just these words, because I don't know, I forget the terminology in English, so how it is called. Примитивный корень, как сказать? Primitive root. I would like to be primitive root. The generator of the multiplicative group of a field, it is better. We can take any k, but it is even better to take this particular k. Okay. Of course, this one normalizes T. Namely, we have such equation. Well, and now okay? One goes. I think this one. Well, this one. Okay. So it actually normalizes the group, and we can do as follows. Let us denote by lambda this conjugation by gamma. So lambda is an automorphism of CP to itself obtained by conjugation by gamma. What we see? We see that if we act on this E to I by lambda and then apply H to I, or we apply H to I from the very beginning, the result is the same, since lambda acts here trivially. So we immediately see that lambda star of E to I minus E to I lies in the kernel of H to I. So our goal is to compute this element. This group is nothing by FP itself. It is just generated by E to I. So if we compute this and we get some, not e to I, but e to I with some other coefficient. Then we succeed to prove that our result is indeed 0. So the question is how to try to compute this. Well, no, this is action on the group. No, it's, yes, action on the group is multiplication by k, but what is action on homology?
It seems that it should be a multiplication by k to the power pi minus 1 for this to work.
No, another power. Sorry.
Not pi minus 1, the power I.
Yes. Well, it is here. Yes, the correct answer is that lambda star e to I is k I e to I. If we see this answer, then the result is immediate. Look, we see that h to I, we see that, assume for a moment that we get this answer. We need to compute this, but why it is enough? The matter is that now we see that k I minus 1 times e to I lies in the kernel of h to I. Well, but if k is a primitive root, so this equals to 0, this coefficient equals to 0, if and only if I is divisible by 2, I is divisible by pi minus p minus 1, exactly as required. So if I is not divisible by pi minus p minus 1, then this is not 0, and then, well, or all elements in a field are invertible, then we get that e to I lies in the kernel of h to I. So this homomorphism is trivial. Well, so this is completely enough. Well, and the only question is how to prove this, how to compute this action. Well, yes, and on that particular projective resolution. Yeah, we get we have this particular projective resolution. Let us write down the action of it. Well, where are polynomials? Well, we just have such a resolution. Here z0. Here is 0 is generator. Here E1. These are not exactly those is. These is are obtained by after tensoring by FP. Yes, but they are very close to them. And what is the action here? So indeed, the idea is that we would like to write this lambda on the level of cochains. So it is on the level of homology. It is usually written by star. Here it is often written by sharp. So the matter is that it is not this. This is not given to us. To us is given only the action on the group. But we would like to invent action on the resolution. Which will be compatible with the action on the group. So if we think about something polynomial, then the question is why is I but not 2I? But it is exactly I here. So our goal is to write formulae like that for even and well, how it is called, and odd, yes, so that the differential remains invariant if we replace e to i's by such elements and groups element by this automorphism. So why we can't write just like that? Oh, sorry. I just would like I remind that we have what is differential in our the matter is that this delta is not invariant under our automorphism. And so our formula for the differential will not be true if we just replace all t by tk, t to the power k. They are false. So we cannot write down like that. With this formula, everything is okay. Sigma is invariant under our automorphism, but delta is not. So we need to write some other. We would like to write here such formula that we want what do we want? We want to have the following properties. We want to see that if we compute these, then it is t to the k minus 1 times okay. And for even, we want to have the same formula. Again, sigma, since sigma is invariant. So we just would like to invent formula for this, for the action of lambda sharp, so that this will be satisfied. And then we need to go to homology and see this formula.
We should multiply by t to the power. So one thought, maybe we should multiply by t to the power minus 1 plus etc.
How? Well,
t to the power k minus 1
oh, what is k? Ah, oh, yeah.
plus etc. plus 1. So the first thing we could be,
Like that.
yeah.
Okay. And okay, it is not enough to have only one part. We need to have two. Then we can check whether it works or not. Here? Since we want This is very close to right answer.
So, so if we have some pilot t, we should take it to pilot t to the power k and put this into the power I. So this bracket we should take to the power I believe, and we should say that I'm not sure how to write it in these terms, like with e, but if we have some polynomial of t, we should take the polynomial, instead of it, we should take the polynomial of t to the power k.
Well,
No, so we have some polynomial of t. Then
Yes.
we
Yes.
take the polynomial of t to the power k and multiply it by the
that's
bracket
right.
power I.
But now we need to do it with these particular polynomials, and the answer is rather simple.
And this polynomial is what? Which one?
Well,
Details.
one small remark. This is true. This is the answer. So we need here to have this one. I have already said that this is true, but we need to have here something to make formulae correct. Actually, this could not be directly true. The matter we could have some powers of t here also, but in fact it is true. It is true directly. Well, I think that's more or less time we need to finish. So I think I will write a correct formula. It is almost written here. we just need to add k to the power I here. Look, I claim that these are correct formulae. Why? Look, if you take the boundary of this odd thing, then this k to the power I, if you take this one, yes, then what we get if we apply sigma, we would like to have things like that, yes? What we get if we apply sigma to this guy? Sigma eats all these powers of t. Sigma multiplied by any power of t is again sigma. So if I would like to write this right-hand side, then sigma applied to any power of t is just again sigma. So what we get here, this can be replaced by k. So we need k to the power I plus 1, this I and this one. Sigma e to I plus 1. And this is again exactly boundary of this one. This one is boundary of k to the power I plus 1 e 2, and okay, this is true. And this one is also true. It is just easy to see that if we multiply by t minus 1, then we get tk minus 1. So our automorphism of the matter is that we can, our automorphism is initially only on the group itself. We need to extend this automorphism to the resolution whenever we like, and the action on homology doesn't depend on the action on this resolution. But okay, we need to extend so that it is automorphism of chain complex. But we extend in this way, and that's all. On homology, we see this formula. So this is general situation. If we have a group, actually, even not the same group. If we have two groups, G and H, yes, and we have a homomorphism of them, and we want to ask how this homomorphism act on homology. What is the induced homomorphism in homology? Then we need to write down a resolution, let it be P, for G, for Z over ZG, and we need to write down a resolution, let it be Q, for Z over, this first one is over ZG, the second one is over ZH. And we would like to find any homomorphism here which okay, here are ZG models, here are ZH model, and we have phi from this ring to that ring. We need to invent any map of resolution which respects this homomorphism. And then this map yields the required action and homology. So we have freedom in choosing this phi, and the action and homology is independent on this phi. This is a version of the result that the homology itself is independent of the choice of a resolution. And the map and homology is independent on the choice of map of resolutions. So in our situation, this is exactly what we did. The only difference is that H is the same as G. So for this phi, we take lambda. For these resolutions, we take the same resolution. And we invent in our notation, this is lambda, this is G, and this is lambda sharp. We invent this lambda sharp so that it is a chain map after applying phi.
Of the sharp acts on polynomials, basically, on this ZCP.
Yes, yes.
And what's E? So first we took E.
Yes,
This is an element of homology. So
yeah. There is, yes, I'm sorry for this notation, but they are standard. We use E to I both for generator of this group and for generator of the quotient of the homology, which is in our case, homology is just these PIs in our case is ZCP, well, and homology is the coinvariance of that CP, which is just Z. We use EI for definition of, so this EI is in homology, but that EI are in resolution.
so that's like T, right?
Well,
That's like T. If we regard ZCP as polynomials over T quotient by something,
yes.
then E to I and the EI, etc., they are all T.
No, they are not T. They are generators of these free modules. And T is polynomial, generator of polynomial ring. They are just generators of these one-dimensional modules.
So they are like one.
Yeah, they're like one, just we want to distinguish between ones in different dimensions. But so we denoted these ones by EI. And we invented such morphism of resolution which computes with this homomorphism of group rings, isomorphism, automorphism. And so we have proved those propositions that almost all operations, except for those, it appears that only those operations can be non-trivial which raise the dimension by such numbers, 2i to the power p minus 1. And they, after some normalization, they can be conveniently taken for standard reduced powers. And that normalization comes immediately from, okay, we can compute, we can take any of those, we want our operations first to compute with, so we have plenty of operations of the following form. We can take u to the power p, well, and take the quotient by sum 2i p minus e 2i p minus 1. We have only these operations can be non-trivial. Here we have two parameters. One of them is I, p is fixed. One of them is I, and another of them is degree of U. We need to unite these operations to now we need to normalize them so that first of all we would like that they commute with suspensions. So we would like to denote by the same symbol PS different operations which for different degrees of U. And then we would like that for degree of U equal to 2i, the result of 2s, the result of operation is just the s power. This is when why this strange coefficient appears. We just compute what coefficient appears from this. So this is some computation in the same spirit. We just compute some, but we will not do it explicitly. But if anybody wants, he can find it, for instance, in Steinert Epstein or in Steinert's original article and so on. Well, and so this is how cohomological operations initially were invented. So this is they initially come from this construction, and later there were different approaches appear. Well, I think that's all for today. Let's stop, and thank you for your attention.